Hello students, welcome to my YouTube channel. In this video lecture, I am going to answer questions 21 to question 30 from sample paper 6 RK Bali navigation book. Now please pay attention, the book that I am referring to is 4th revised edition of Air Navigation RK Bali. So there are different editions, 4th edition, 5th edition, I guess 6th edition is also there. So I have taken questions from the 4th edition book. Now the questions are not very different among the books of fourth edition, fifth edition, sixth edition. So not very different questions. The question papers are the same. So don't worry. Even if you practice these questions, it will do you good. So let's start with question number 21. There is distance 123 nautical miles between points X and Y. Flight level is given. Temperature outside is given. Headwind is given to you. What is the required rectified airspeed to fly from X to Y in 42 minutes? Right? So we have to find out the calibrated airspeed. Okay. So distance 123 nautical miles. Time 42 minutes. If time is 42 minutes, ground speed will be distance by time. So 123 into 60 divided by 42, that is equal to 123 into 60 divided by 42, correction, is 175.7 nautical miles or 176 knots, correction, 176 knot. Now if ground speed is 176 knot, headwind component given to you is minus 25. So true airspeed will be equal to ground speed minus headwind. So ground speed 176 minus 25 is 151 knots. 151 knots. Okay. So you have task given to you. You have flight level given to you. You have outside air temperature given to you. Now let's go back to CX3. Option number second, airspeed option. Task is 151. Outside air temperature in degrees Celsius. Make sure the units are correct. Plus 7 degrees Celsius. So positive 7. Pressure altitude given to you is 13,000 feet. So in this scenario, the calibrated airspeed that you get is equal to 120 knots. Is equal to 120 knots. So the options here are 160, 165 and okay, task will be 176 plus 25, 201. So my bad. Make sure it should be 201 knots. We have to add it. Now in a headwind component, where your aircraft is going to fly at a particular true airspeed, whenever it encounters a headwind, the ground speed will be less than the true airspeed. Whenever it encounters tailwind, the ground speed will be more than true airspeed. So here we already have ground speed of 176 knots. Now this ground speed will be much less than true airspeed because of the presence of headwinds. So add that. So let's put this 201 here. Task 201, 7 degrees Celsius and pressure altitude 13,000 feet. So calibrated airspeed is 160.11. So the closest option is option A. So question 21 is option A. Next, the aircraft is steering magnetic heading of 155. RMI reads 330. Which way would you turn to intercept magnetic 140 away from the NDB station? What would RMI show whenever you intercept that track away from the NDB station? Now do watch my VOR, ADF, RMI chapters. I have solved all the questions related to them from RK Bali, Oxford and Keith Williams. So if you watch those video lectures, you will be very thorough with the concept of RBI, ADF, VOR, HSI, RMI, and you will be very confident, definitely. So do watch those video lectures. So I will explain that concept in short here. RMI is nothing but a radio magnetic indicator. Okay, radio magnetic indicator. Radio magnetic indicator gives you three things. First, it displays magnetic heading of aircraft. Second, QDM or magnetic track towards the VOR station. Third, QDM or magnetic track to the NDB station. So it doesn't show relative bearing. It directly gives you the track that you must fly to go directly towards the VOR station, NDB station. So you have a provision for magnetic heading here. Let's say there will be one needle and there will be another needle. Okay, so I'm going to paint it like this. So let's say this needle belongs to VOR and this belongs to NDB. Now the tip of this VOR needle will will give you the information of QDM towards the VOR station. The tail of this needle will point towards or give you the information of track that you must fly from the VOR station. Similarly with NDB, the head of this needle will point towards the track, will give the information of track that you must fly to go towards the NDB station, and the tail of this needle will give you the track that you must fly away from the NDB station. Okay. Now in this question, heading is 155, magnetic heading is 155, and RMI indication, in other words, QDM indication is given 330. Is given to you 330. If QDM is 330, QDR will be reciprocal of that 150. Okay, so let's say here is your NDB station. This is the north datum. Radial 150 is there. Radial 330 is there. Okay. Aircraft heading is 155 and QDM is 330. That means this is your aircraft. The heading is 155, 5 degrees more than 150, and QDM to the station is 150. QDM to the station is 150. QDM to the station is 330. Correction. QDM to the station is 330 and QDR is 150. Okay. So my bad. We will draw this here. Okay. QDM to the station is 330 and aircraft is pointing at 155. So that means QDR, that is track away from the NDB station, is 150. Correct? That means aircraft is on track 150, heading 155, and QDM or track towards the station is as given in the question 330. 330. Now the question states Which way would you turn to intercept magnetic track 140 away from the station? Now magnetic track 140 will be this track. I am writing it R140, radial 140. I know that NDB stations do not transmit radials, but still it's radial, just for simplicity, it's track 140 or radial 140. So now from this position, you have to go to that position, that is 140, track 140, and then you have to fly that track 140 inbound, outbound as given in the question. But question has just asked you which way would you turn to intercept a track of 140 away from the station or outbound from the station. Now look, you are on track 150 outbound from this NDB station. Your current heading is 155. That means towards the south westerly direction. Okay, towards the south direction. And you want to go to track 140. So in order to go to track 140, you will have to make a left turn, because that will be the shortest turn you will have to make in order to go towards that direction. So you will make a left turn, in order to intercept a track of 140 from the NDB station. So it is so it's either option Bravo or option Charlie. Next, what would RMI indicate at the point of interception? So whenever you complete this left turn and you are somewhere positioned, you're positioned somewhere on this radial 140, like this. So what will the RMI indicator indicate at this point of time? So the work of RMI is to always point towards the NDB station, to always give you the information of the track that you must fly towards the NDB station. So when you are at radial or track 140 from the NDB station, the reciprocal track will be track 220 from that NDB station. So whenever you intercept that track, the RMI will point towards the NDB station like this. RMI indicator will point towards the NDB station like this. Okay, and it will point. So if you are at track 140 outbound, the track towards the NDB station will be reciprocal of 140, which is 220, which will take you in that direction towards the NDB. So QDM should be somewhat correction. The reciprocal of 140 is 320. Yeah. So it is 320. So your RMI will indicate a direction of 320. That is, this direction is nothing but the track that you will fly towards the NDB station. So the correct option here is option Charlie. First, you will have to make a left turn in order to intercept a track of 140 outbound. After making a left turn, and whenever you intercept that track, the QDM will be 320. Okay. So option Charlie is the correct option. Question number 23. An aircraft is on its final approach. Okay, so let's draw this diagram for better understanding. Let's say this is your runway. An aircraft is on the final approach. That means it's within 5-6 nautical miles of the touchdown zone of this runway. Okay, somewhere here. The ILS indicator shows 2 dot left indication and 2 dots above the line indication. So let's say this is your ILS indication here, and this is a 4 dot indicator. Okay, 4 dot indicator either side. Now the 2 dot left indication. So that means 2 dot left indication is this, and 2 dots above the center line indication. So that means 2 dots above the center line indication is this. Okay. This is the indication given by the CDI indicator in your aircraft. Now, like I always say, CDI indications are nothing but the solutions. Solutions to what problem? Solutions to a problem of aircraft deviation from its intended track. Aircraft deviation is the problem. That means if CDI tells you to fly left, a fly left indication, aircraft aircraft is to the right of the center line. Aircraft is to the right of extended extended center line. If the CDI is asking you to fly two dots above up indication, that means aircraft is below the glide slope. Is below the glide slope. So that is the reality, and therefore the solution to that problem is fly up. By how much amount? By an amount equal to two dots. Now two dots equal to how much angular deviation? We will find that out. Now as a rule, in a four dot indicator, one dot will be equal to 0.175 degree for a glide slope. One dot will be equal to 0.625 degree for a localizer. 0.625 degree for a localizer. Okay, next, you are 3 nautical miles from the threshold. So you are 3 nautical miles from the threshold. ILS has a 4 dot scale. Find distance from extended runway center line and the height of aircraft above the threshold. That means you have to find out how much. So I will draw 3 diagrams here. The first one for localizer. So let's say this is your runway and this is the center line of that runway, extended center line. Now your aircraft is somewhere to the right of this center line. It needs to be correctly established on the extended center line, but it is to the right hand side of it, and therefore the CDI is asking the pilot to fly left, two dots left. So now the question has asked us to find out the distance aircraft has deviated from this extended center line. Okay, the distance. Now this distance can be angular as well as in terms of nautical miles. So here we have to find out the distance in terms of meters, nautical miles, etc. Okay, now, so first let's address the localizer part. Two dots is equivalent to 2 into 0.625 degrees. So 2 into 0.625 degree is 1.25 degree. That means aircraft has deviated 1.25 degree to the right hand side of the localizer center line. Correct? 1.25 degrees. And it is 3 nautical miles from that threshold of the runway. So to resolve this figure, we have a triangle whose one side is 3 nautical miles. Angle is 1.25 degrees. This is 90 degree. Position of this aircraft is here, right? I have drawn this triangle here. And now we have been asked to find out this particular x distance, the distance aircraft is away from the localizer center line. So we can apply cos theta formula. Cos theta is adjacent. We will apply tan theta formula, which is opposite side upon adjacent side. Opposite side is x, adjacent side is 3 nautical miles, tan of 1.25. So x will be 3 nautical miles, convert that into meters. 3 into 1852 meter into tan 1.25, that is 0.02. So x equals to into 3 into 1852, that is 121 meter. So x is 121 meter. So the options here are 115 meters right of center line, 115 meters left of center line, 230 meters right of center line. So we already know that aircraft is to the right of the center line. So we will eliminate option number Bravo because it says that aircraft is to the left. So we are remained with options A and C. One is 115 meters right and another is 230 meters right. The answer that I have got is 121 meter to the right hand side. Now 121 meter is pretty close to option A, 115 meters to the right hand side. But before marking that option, now we will find the distance aircraft is below the glide slope. Aircraft is below the glide slope, and we will check the value that we get, and then we will come to a conclusion whether option A is really the right answer or we have made some error somewhere. So for glide slope, I am going to draw this perspective. This is the 3-degree standard glide path. Aircraft is expected to be on this 3-degree glide path, but it is below that glide path somewhere here. Okay, it is below that glide path. It is below that glide path, and we have to find this vertical distance. It is below that glide path. The angle. Okay, so just a second. So I'll draw a neat diagram. This is 3-degree. This is the ground surface. Aircraft is here. The glide path is this. So we have to find this vertical distance, this total distance. This is the original glide path. Okay, I'm labeling it. This is your original 3-degree glide path that aircraft must be following. But aircraft is little bit below that glide path. So the glide path that aircraft is actually following is only this much. Okay, this much. So this is totally 3-degree. We have to subtract this small angle from that total 3-degree in order to get the glide path that aircraft is actually following. Okay, in order to get this particular small angle. Now, one dot equals to, in case of glide path, 0.175 degrees. Aircraft is 2 dots deviated. So 2 dots will be equal to 2 into 0.175, 0.35 degrees. That means aircraft is 0.35 degree. This value is 0.35 degree below 3-degree glide path. So 3 minus 0.35 amounts to 2.65. So aircraft is 2.65 degrees above the ground surface. So that means aircraft is actually following a glide slope of 2.65 degrees instead of following a glide path of 3 degrees. So now we have a triangle here. That angle of the inner triangle is 0.35 degrees. Okay. We have to find the vertical distance x. An aircraft is 3 nautical miles away from the threshold of the runway. Aircraft is 3 nautical miles away from the threshold of the runway. So let's apply again tan theta formula. Tan theta is opposite side upon adjacent side. So tan of 0.35 is opposite upon 3 nautical miles, 3 into 1852 meter. So x will be 3 into 1852 into tan 0.35 degree. So 3 into 1852 into tan 0.35 is 33.9 or 34 meter. That means aircraft is 34 meters below the correct glide path of 3 degrees, 34 meter. So let's check the options here. Option A says 115 and 45 meters. We have got 34 meter. So I'll go with option A because it has the values which are closest to the values that I have found. Okay. Question number 24. Airborne Doppler equipment is most likely to unlock over a calm sea. Do read the Doppler radar chapter, very important. After takeoff, VNAV. VNAV is nothing but vertical navigation. VNAV is vertical navigation. So this vertical navigation will be explored much more in detail when I start doing my type rating lectures. I will teach all that in those lectures very soon. And whenever you go for type rating, this will be very relevant to your syllabus, to your training. VNAV, LNAV. VNAV is vertical navigation. LNAV opposed to that is lateral navigation. So let's say your aircraft is on the runway. Aircraft is on the runway. Where it is positioned on the runway ready for takeoff, or your primary flight display, there will be the top column reserved for autopilot commands, autopilot information. So you will have LNAV, VNAV written there. So let's say LNAV, VNAV is written here. So when you are on the ground, this LNAV, VNAV modes remain in engaged modes. That means they are not yet active. They will soon become active once you become airborne. Now, once you become airborne, you are expected to follow a particular departure profile. Let's say first departure profile is 2500 feet. Okay. After flying to 2500 feet, you are expected to fly level for some time. Then again 5000 feet and level. Okay. Again fly higher 10,000 feet and level. So vertical navigation, VNAV mode of your autopilot is responsible for navigating your aircraft with respect to the vertical constraints. That means whatever vertical limits are imposed on you, whether by the ATC controller or by the SID departure chart. So whenever your aircraft becomes airborne, automatically this VNAV mode will engage, become active. And you will see that written on the top of the primary flight display, VNAV, green. Okay, you will see that written on the primary flight display in green. That means the flight management system knows all the vertical limits that are going to fall along your route. So over here 2500 feet, 5000 feet, 10,000 feet. So this vertical navigation will become active. Okay, and it will automatically, whenever you engage the autopilot, the aircraft will automatically fly towards that altitude. And when you approach this 2500 feet altitude, your aircraft will automatically start maintaining this altitude up to this point. At this point, again, this VNAV will become engaged and your aircraft will start climbing towards 5000 feet. Then fly level for some time and then again climb towards a higher altitude of 10,000 feet and then follow that altitude. So this VNAV mode, just to explain in simple words, is responsible for maintaining all the altitude constraints or all the minimum IFR altitudes specified for that particular route, and this will be shown on your primary flight display whenever VNAV is engaged, VNAV is active. Okay, so all this information will be provided to you. So a thrust setting other than takeoff power is set and altitude selected is initially above aircraft current height. So correct option is option A. Always the altitudes that you are going to fly towards must be higher than your previous altitude or your current altitude. Only and only then this VNAV mode will be engaged. In your descent, this vertical constraints altitude will be below the altitude which you are currently flying or you have been flying. Okay. So a thrust setting should be other than takeoff. After takeoff, Obviously, whenever you complete your takeoff, as a part of your takeoff after takeoff procedure, you bring back the thrust levers, or if you're flying ATR aircraft, you bring back the power levers back, okay, to your cruise mode or whatever procedure that you follow. So you do not need a full takeoff thrust when you have completed your takeoff. So you bring it back to a smaller amount. And the altitude selected is initially above aircraft height. It is the pilot's responsibility to keep changing the altitude constraints. Okay. Next, question number 26. Aircraft flies the following rumline tracks and distance from position. So beginning position is 4° north, 30° west. I have solved so many similar questions from RK Bali, Keith Williams, Oxford. So watch those lectures also. So you are starting from 4° north, 30° west, and then you are flying 700 nautical miles south. So it will be helpful to draw this diagram of the earth, and next to it I will draw a horizontal representation of the earth as well. So this is the north datum, this is the north datum, this is your equator, this is your equator. So current position of aircraft is 4° north, 4° north, 4° north, and the longitude is 30° west, 30° west. Now from this 4° north position, it flies 700 nautical miles southward. It flies 700 nautical miles south direction. South direction. Okay. Now whenever your aircraft flies north or south along a constant longitude, it is actually flying a great circle track. So we are going to apply great circle formula here. Great circle distance is equal to d lat into 60. So distance already is given to us. The difference between two latitudes can be found out. So d lat will be 700 by 60, that is equal to 11 degree 40 minutes. A difference of 11 degree 40 minutes towards the south, towards south direction. So now the total 11 degree 40 minutes will be spent in traveling first 4° here, and the remaining down in the south hemisphere. So 11 degree 40 minutes minus 4° is 7 degree 40 minutes. So extra 7 degree 40 minutes will be spent in the southern hemisphere. South. So your next position, your new position when you fly south will be 7 degree 40 minutes south in the southern hemisphere. From this position, you fly 700 nautical miles east. You fly 700 nautical miles east, like this. Like this. So when you fly 700 nautical mile east, you will be intersecting or crossing a new longitude. You will be crossing a new longitude. This is 700. So now when you fly along a fixed parallel of latitude, along a parallel of latitude between two different longitudes, you are actually flying a rumline distance. You are actually flying a rumline distance. 700 divided by cos latitude is 7 degree 40 minutes into d long minutes. Correct? The latitude here is 7 degree 40 minutes south latitude. So cos of 7 degree 40 minutes is equal to 0.99. So 700 divided by 0.99 is 707 minutes, which is equal to 11 degree 47 minutes. When you divide it by 60, you get answer 11 degree 47 minutes. So now the current longitude is 30 degree west. When you travel 11 degree 47 minutes easterly direction, your new longitude will be 30 degree minus 11 degree 47 minutes, which is 18 degree 13 minutes west. You are in the western hemisphere, and when you travel easterly in the western hemisphere, the values of longitudes decrease. So your new longitude is 18 degree 13 minutes west. Now from here you again travel 700 nautical miles north. So from here you again travel 700 nautical miles north. So again this will be your great circle distance. This will be your great circle distance. D lat divided by multiplied by 60. So d lat in degrees will be equal to your distance by 60. 700 by 60 is 11 degree 40 minutes towards north. Towards north direction. So your new latitude will be this old latitude. This latitude of 7 degree 40 minutes south, and the difference is 11 degree 40 minutes. So 11 degree 40 minutes means out of total 11 degree 40 minutes, you are going to spend 7 degree 40 minutes in traveling from this latitude towards the equator. 7 degree 40. So the remaining latitude distance will be equal to 4 degree. 4 degree north. 4 degree north. So you have come back to the same latitude that which you from where you started your journey. 4 degree north, 4 degree north. Now from here you again travel 700 nautical mile west. You travel 700 nautical mile west. Correct? So when you travel 700 nautical mile west, the chances are you may end up somewhere before this point, or you may end up somewhere beyond this point, because on the real earth, on the earth, what happens is longitudes converge. The convergence is maximum at poles. The convergence is maximum at poles and minimum at the equator. Convergence is zero at the equator. So as latitudes increase, convergence increases. The value of convergency increases. Now here we have two different latitudes. One is 4 degree and another is 7 degree 40 minutes south. Now 7 degree 40 minutes south latitude is more in value than 4 degree north latitude. So if latitude value is more, that means the convergency found at that particular latitude will be more. So that means convergency here will be less than convergency here. So that means when you travel 700 nautical miles at this particular latitude, 7 degree 40 minutes south, when you fly 700 nautical mile east, so the distance that you cover here will be much more than the distance that you are going to cover here. So when you travel same 700 nautical miles in the northern hemisphere, you will end up being somewhere here. Okay, you will not cross this particular longitude, because the distance at 4 degree north latitude, the distance between two longitudes will be much more than the distance between two longitudes at 7 degree 40 minutes 7 degree 40 minutes south latitude. 7 degree 40 minutes south latitude. Okay, so I'll prove that to you. Let's use Ramline distance formula. Ramline distance is d long in minutes into cos lat. So d long in minutes will be equal to 700 nautical miles divided by cos latitude 4 degree. So cos 4 is 0.99. So 700 divided by 0.99 is 707 nautical miles. Correction, 707 minutes divided by 60 is 11 degree 47 minutes. 11 degree 47 minutes. So current longitude is 18 degree 13 minutes west. From this longitude, when you travel westwards, new longitude will be old longitude plus d long. Old longitude is 11 degree 47 minutes plus Original longitude 18 degree 13 minutes. That is 30 degree, okay, approximately 30 degree. Now 30 degree west longitude is again the same longitude as this. So the correct answer will be, frankly speaking, it should be less than 30 degree west longitude for the only reason I explained you here, convergency. Okay, but here the approximate value we are getting is 30 degree. Now the latitude is going to remain the same, 4 degree north. So let's eliminate option Bravo. We are left with options Alpha and Charlie. Option Alpha is 30 degree 3 minutes west, more than 30 degree west. Option Charlie is 29 degree 55 minutes west, less than, so 5 minutes less than 30 degree west longitude. So it will be best to select option Charlie, because we know, because of the concept of convergency, a new position here ought to be before this 30 degree west longitude, not beyond it. Okay, so although this is 30 degree west, but remember, whatever value we will get here will be the approximate value. The values given in the options may not match with the accurate value in your calc. So in such times, you are going to apply this conceptual understanding and mark the answer. Question 27. Task is given, course, winds, descent is initiated, is given, distance is given, what is approximate rate of descent. So your aircraft is descending from a particular altitude to a lower altitude. So it is descending from an altitude of 22,000 to 4,000. Okay. So it is descending. So change in height is equal to 22,000 minus 4,000, 18,000. The distance that it covers during this descent is equal to 39 nautical miles. We know that rate of descent equals to change in height divided by the time that it takes to descend in minutes. Okay, how much height you are going to descend in what time limit? So change in height we know already, 18,000. Now the time, we do not know time, but we do know the distance, and we know the speed of this aircraft. What we know is TAS, we have the winds, we have the true course given to us. Okay, using this information, we can find out ground speed of this aircraft. Now, how to find out ground speed? Ground speed is nothing but your true airspeed minus headwind component, or it can be true airspeed plus tailwind component. So we do not know yet whether we are experiencing a tailwind or a headwind. So for that, to determine that, let's draw this diagram. You are following a course of 240. This is the north datum. Your aircraft is following a course of 240. Winds are originating from 18030. So that means winds are direct crosswind, direct from the south direction. Okay, but this is not a complete crosswind. This is not a 90-degree crosswind. So this wind is made of two parts. Some crosswind component and remaining component belongs to headwind. So now let's find out the headwind component using the formula. Headwind component equals to, minus stands for headwind, wind speed into cos theta, where theta is equal to difference between your wind direction 180 and the course that you are flying 240. So that is minus 60. Okay, wind minus course. So that is cos minus 60. Wind speed is 30 knots. So now cos minus 60 is half. Cos 60 is essentially half. So that is 0.5. So 30 into 0.5 is 15 knots. And now we have minus sign and minus sign, correct? So 180 minus 240. So minus minus is plus. Okay, so we are getting a tailwind of 15 knots. So your ground speed will be true airspeed 197, tailwind 15. So 197 plus 15 is 212 knots. 212 knots. Okay. So time taken will be 39 nautical miles divided by 212, that is 11 minutes. 11 minutes. So rate of descent will be 18,000 divided by 11, that will be equal to 1,636 feet per minute. The closest option here will be option Bravo. You cannot fly 1,636 accurately. The closest number will be fly 1,600 feet per minute or 1,500. So option Bravo. Next. Distance Q to R is given to you. Ground speed outbound, ground speed homebound, endurance is given. We have to find out distance to the point of no return. So distance to the point of no return equals to outbound ground speed into homebound ground speed into endurance divided by outbound plus homebound. So outbound speed is 495, homebound is 465, endurance is 9 hours, 495 plus 465. So now 495 into 465 into 9 hours is 2071575. 495 plus 465 is 960. So 2071575 divided by 960 is 2157.8 or 2158 nautical miles. So option Charlie. Formula based question. Question number 29. The effect on the position of the critical point of reducing the task in a headwind component will be to what? So let's say this is your point alpha, point Bravo, and there is critical point somewhere here. Your aircraft is flying from A to B, and this is still air conditions. The conditions that you are flying in are still air conditions. That means calm winds, no headwind, no tailwind, no crosswind. Now in scenario number 2, I am putting some amount of headwind component in this scenario. So that means your aircraft is going to encounter headwind as it flies from point A to point B. Now then, this is one important property of critical point or point of equal time, that the critical point will always move in the direction of the wind. So that means it will move into the wind, the direction from where the wind is blowing. So if wind is coming from right hand side, meaning it's a headwind to aircraft flying from A to B like this. So the CP or the critical point will move towards that direction. So originally the critical point was here in nil wind or zero wind conditions. But in headwind, this critical point will be somewhere here towards into that direction. If now let's say in scenario number 3, you are getting tailwinds. In that conditions, in tailwind conditions, your critical point will move into the direction from where the wind is coming. So if the wind is coming from left hand side, meaning it's a tailwind condition, the critical point will move from this position, the center position, to that new position towards the tailwind. So now here we have been given a headwind component. So in a headwind component, the critical point will move into the headwind. So what has happened? The distance between alpha, your departure, and critical point has increased. It's increased by this much amount, x. In tailwind conditions, the distance between your departure and critical point will decrease. So here will be, so what will happen? So in headwind conditions, your distance will increase. Your distance over here in zero wind conditions, the distance was, let's say, 100 nautical miles. In headwind conditions, this distance will be this 100 plus this extra amount x. So 100 plus x, that x can be 10, 20, whatever. So it will increase your distance towards the critical point. Last question, number 30. Air temperature is given to you. What is local speed of sound? Local speed of sound is 39.17 square root of temperature in terms of Kelvin. So if temperature is 20 Celsius, in terms of Kelvin, it will be, Kelvin is nothing but Celsius plus 273. So if 20 degrees Celsius is given, so the temperature in Kelvin will be 273 plus 20, 293 Kelvin. 39.17 square root of 293, 17. So 39.17 into 17 is 670 knots. So option bravo. You can use this CX3 also. So if outside temperature is, let's say, 20 degrees Celsius, so yeah, so no, local speed of sound cannot be found here. You can find TAS, you can find Mach number, but local speed of sound, I don't think so. Speed, yeah, yes. You at least need another component like TAS or Mach number to find out local speed of sound. So nevertheless, this is the formula. Use this formula and find the answer. So I'll stop here. I hope you have understood all the 10 questions that I answered, explained, elaborated in this particular lecture. If you have any doubts, any comments, feedback, let me know in the comment box. Keep practicing these questions again and again. And do watch the video lectures that I have already uploaded to my YouTube channel. All the lectures related to VOR, ADF, RMI, 1 in 60 rule, so many lectures. So do watch them and revise your concepts, resolve your doubts, and answer all your questions. So thank you for your time. Share this video with all your friends, please. And if you haven't subscribed to this channel yet, do subscribe to it and hit the like button if you have liked this video lecture. All the best.